All right, it's time. So let's continue. Before, any questions from the homework? Nick?
Yeah, can you go over 6.2 number 6 and 6.3 number 4?
6.2, number 6. All right. 6.3, number 4. What we have is we have a region. And we want to rotate this region about x equal to -2. So let's draw this first. It's this region rotated by this. So after you do that, you will have something like this. Okay. You were wondering what the volume is, and you want to use the washer method. All right. So what we have here is you need to first determine, do you want to do dx or dy? If you do dx, you cut things in this way. Then you rotate it. Can you see that? If you do dx, you will have a shell. So in order to get a washer, you have to cut it horizontally. So that's the first step. Take this one and cut it horizontally. Therefore, it's dy. You go from 0 all the way to here. And that, you can solve it. You plug in x equal to 4. You got 64. So this is 64. Now what you want to put here is going to be the washer. Pi r square minus pi r square. Okay. Now if you draw it, the capital R goes all the way from here to here, and the small r goes all the way from here to here. So the capital R is going to be 4 plus 2, which is 6. The small r is going to be x, which is from here to 0, and then plus another 2. Finally, you cannot take this because everything should be in terms of y. So you should try to rewrite x on this parabola, and implies x equals square root of y over 4. So replace this one by otherwise you cannot do the integral. Okay, that will be the setup for question 6. The rest will be doing the integral, and it's not going to be easy. So try your best and use a calculator if necessary. I'm pretty sure you can get the right answer. It's just the decimal. The decimals are impossible to calculate use by hand. All right, that's number 6. Now 6.3, number 4. You have a region rotated by, okay. You have this region rotated by y equals -4. You want to use the shell method. Okay. Okay. Y equals 9x y equals y minus 9x. Y equals 0, so this part rotated by y equals -4. So after rotation, you will have some shape like this. Okay, that will be the drawing. Now what you want to do is you want to do the shell. Again, try to draw the shell first. Okay, if you draw this after rotation, this will be a shell. If you draw this after rotation, this will be a washer. So clearly we want to do things in shell. We want dy. Okay, we want to integrate from 0 to here. And that is where these two lines intersect. So 9 minus x equals 9x. This implies x equals 9 over 10. This implies y equals 9 minus 9 over 10, which is 10 over 81. Okay, 2 pi. Now you want r and h. Now to draw it, I think it's easy to see r is given by this and h is given by this. So r is easy. R is going to be y plus a 4. Your h is going to be how long this thing is, and that is the difference between the two lines, right? And you need to use the right minus the left. Which one is on the right? 9 minus x is on the right because it's going down, right? 9x is on the left, so you should use this minus that if you do dy. So finally you realize in order to do dy, I cannot take x, I cannot take x, I need it to be y. So that's the rough idea. This one on the right, this one on the left, but moreover, you should switch them into y. So 9 minus y minus y over 9. Okay, that will be how you set up the whole thing before you take the integration. All right, Julia?
Yeah, I don't have anything about web work. I was just wondering if you could maybe post the notes from last Thursday and Friday when you get a chance.
Okay, I forgot to do it again. Let me make sure. It's December 3rd and 4th. I better have it. Okay, I have it. Yeah, I can post it by tonight.
Okay, thank you.
Thanks. Other questions from the homework? Adam?
Is it okay if we use like Desmos or something to look at the graph, or do you have some method you want us to show
For
you
the,
on the test?
for the web work, it's totally fine. But for the
Okay.
test, you should be doing hand drawing because drawing things by hand is kind of a skill you should have. You don't need
Okay.
everything to be accurate. For example, like what I draw here, right? You just need a rough idea. Like this is roughly what we have. But technically, for 9x, what you should draw is something like this, right? Which is super ugly. So what I will say is just like draw something that makes sense. You don't have to draw it super accurately. But of course, the more accurate you can draw it, the better understanding you can have for yourself.
Okay.
Okay. But for me, as long as you draw something which looks like a line and a line, for this case, I would take it.
Sounds good.
Yeah.
Thank you.
All right. If no question, let's continue. 2 more sections and we're over. 6.4 is going to be work. We're coming from physics. Does everybody know the concept of work? Okay, so it's something from physics. Let's say you have some cart. You want to push it with 40 Newton with a force. Okay, you push it super hard or super easy, whatever. You push that thing for a distance, which is 20 feet. Then you did something meaningful. Okay, I'm going to call that thing work, which is basically W stands for work equals force times distance. Okay, which is very easy to understand. So your work is proportional to how much effort you make, which is the force, and how much consequence you achieved. Okay, for example, if you have a force with 40 Newton, you push something for 20 feet, you do some work. Now you double the force. You push something with 40 Newton, which is double the force before. For the same distance, you double the work you do. Sounds good? Okay. The other way around, if you use something with a constant force, you push down the cart for 20 feet, and then you use the same force to push it for 40 feet, which is double the distance, you double the work you do. Okay? Now, what if you take a lot of effort, but the thing didn't move? Then you do zero work. Thanks for your effort, but it's a totally waste. You do zero work. Okay. Similarly, if you got a car which is moving for 20 feet, but you sit on the car, you never applied any force. Then you did zero work, even though the car is moving. Sounds good? So force and distance, you need both of them. That's the concept of work. With this thing, you can quantify a lot of things. For example, if you lift a rock, okay, which is 20 kilogram or something, you lift it up for 40 meter, okay, using a crane or something for construction, you do a lot of work, okay? And that amount of work will be used to build the crane machine itself because you need that thing to have a certain kind of capacity for doing a certain amount of work. So it's a very useful concept. Sounds good? Okay. Later you will actually learn, or maybe you have already learned, work is also a way to exchange energies between two things. Okay, so work is basically equivalent to energy in this way. For units, force and distance, and then work. In the United States, for force we use pound, for distance we use feet. The work we do is actually pound and feet. Put a dash line to say they multiply together. United States is the only country who does this, as far as I know. Okay, so if you ever want to do anything in physics later, try to get used to international metric. Force is measured in Newton, distance is measured in meter, and then the work is measured in joule. Okay, so in our class, which unit you take really depends on which unit did you get from the force, which distance unit you get from the feet. All right, that is good. An easy concept. Now, we will handle something more complicated. Let me write it down, the complete problem, and we will do this. A 40 Newton force is required to hold a spring that has been stretched from its natural length of 10 centimeter to 15. Okay, now question, how much work is needed? In stretching the spring from 15 to 18. All right. So to know the work, you just need to know two things, right? Force and the distance. That's all. So you have a spring. It was at 15. Now you want to stretch it to 18. Okay. How much work has been done during this process? How much have you moved? 3 centimeter. Very easy. Okay. What's your force? Now can you see the trouble? Right? The force is not a constant. At 15, you have a force. At 17, you have a stronger force. At 18, you have the strongest force. Okay, so as you move forward, your force is actually increasing because the spring is actually trying to pull you back. The more you go, the bigger the resistance. Sounds good? So in this way, you cannot do it because your force is changing. That's why you cannot simply take a force and times it, because you don't know which force to take. Okay, and that is our next challenge. How do you still do work in this situation where your force or distance may not be a constant? Well, let's see how do we do it. It's changing. All right. This is from 15 to 18. If it's a constant force, I just use 40 times 3. Done. Okay? Now, it's changing. What if it changes by 2 parts? On this part it's 40, on this part it's 50. Now I just use 40 times 3 over 2 plus 50 over times 3 over 2. For 2 period, 2 different force. Sum them together. 2 different part of work. Still okay? Now, of course, the force is not changing suddenly. Then let's divide it into 10 pieces. On this one, maybe you have a 40. On this one, maybe you have a 41. This maybe you have a 42. Eventually, you change to 50. At a different interval, you have a different force. Then what do? You just take 40 times 3 divided by 10 plus 41 times 3 divided by 10, because every single force only apply for 3 divided by 10 if you divide it by 10 parts. Still okay? Now, what if your force is not changing by 10 times? If your force is changing by 1,000,000 times, 1,000,000 intervals. What if your force is changing continuously? Can you see where this is going? You divide them into n parts. Not 2 parts, not 10 parts, n parts. How much work does each? Then you have a lot of different forces, right? Then what you need to do is just sum all the work together. For each force, it only works for this much, which is B minus A divided by N. If you divide it by N parts, which is 18 minus 15 divided by N, 3 over N. Good so far? Now what you need to do is you just need to put the force there for that corresponding interval. Okay? On that corresponding interval, because your force is changing continuously, you don't have a uniform force. It's actually smaller and bigger at different location, but you just treat it as the same, which means you have a different force on this interval, but you just say it's the same force on this interval. Okay, do you realize what this is? Riemann sum. Okay, what you have here is exactly xi star. It's not a constant force, but I just treat it as a constant. So in this way, I have a rectangle. That will create a problem, but it won't be a problem if you let n goes to infinity. Sounds good? Okay, so with that in mind, we have the new formula. That is integration from a to b, f, which depends on x, dot dx. You just sum all the works together. Okay, that's how we do it. If your force is changing. Sounds good? Okay, that's the idea, the main idea for this section. So let's see, how do we do the spring problem? Now it become clear. I'm going to call this direction x, and we only need one dimension. What's the total work? It's going to be integration from 15 to 18. The work for each part. What's the work for each part? Well, each one works for dx. That's the distance. Now what do I need here? I just need the force. By the way, at a different location, I should have a different force. It should depend on x. So what I'm looking for is a function of force depending on x. If I put it here, I have the force, I have the distance, I have the work for that particular piece. Then doing integration is nothing but summing them together. Make sense so far? So there's only one thing left. How do you find the force depending on where you are in the location? Well, let's see it. Why do you have a force? Well, number one, if you stay at a natural length which is 10, you should have no force. This thing just stay there. Okay. Now, if you stretch it to x, now you have a force because the spring is trying to pull you back. Still okay? Do you know the force formula for the spring force? Something called Hooke's law. If no, it's fine. It's given by F equals kx. Okay, what is it? Well, let's think about it. The spring was originally like this. Now what do? You stretch it to here. Okay. So number one, the further you stretch the spring, the stronger the resistance. Match your common experience. You just move it a little, you barely feel anything, but if you try to stretch it, it's harder and harder, to pull it away. So the force should be proportional to x, where x is how much you stretched from the relaxed position. The bigger the x, the stronger the force. Good so far? Cool. Now second, for the same amount of stretching, if you take a very little tiny baby spring, you stretch that thing for 2 centimeters, you receive a resistance. Or you take some industrial standard strong spring, which is this big, you stretch that thing for 2 centimeters. Which one requires more force? Definitely the second one. So it is also related to how strong your spring is. For different spring, to stretch for the same amount, you need different force. And that is characterized by this spring constant here. Sounds good? Okay, so let me write it down. F is force. K is the spring constant. A steel spring is certainly stronger than, I don't know, a copper spring, and maybe it's stronger than a plastic spring. Okay, and it also depends on how many reps you have. X will be the distance from the relaxed position, or as indicated in the problem, from the natural length. Natural means it's not stretched or it's not compressed either. Okay, they mean the same thing. Sounds good? So what's the force if you stretch the whole thing for x? That's definitely going to be kx. Going from 10 to x, how much did you stretch? X minus 10. For example, at 11, I stretched for 1 centimeter. At 15, I stretched 5 centimeter. Still okay here? So the only thing missing is, what is your K? Okay, that is how strong your thing is. Now, if you go back to the original problem, you do have the information. If you stretch that thing from 10 to 15, you need 40 Newton. Right? So that's 40 Newton for 5 centimeter. So how much force per centimeter? 40 divided by 5, which is 8. Okay, so let me write it down. From the problem, if I plug in if I plug in 15, I should use 40 Newton. This implies K equals 40 over 5, which is 8. 8. And finally, this is the force, and that is the distance. Anton?
Wait, does it not matter that the x values do they have to be in meters or centimeters for the, like, would that matter?
That should matter. So when I finish the work, my unit will be actually, okay. If you finish this, I will skip it. It's 156. But the unit is going to be centimeter times Newton,
Okay.
which is 1.56 joule, which is meter times Newton. So you need to do the conversion after that. Otherwise, you change this to be 0.15 and 0.18 if you want to do everything in meters. Okay, so it's really a matter of which unit do you want to use. You can do it before or after. Very good. Okay, so here I skipped. You can do it yourself. It's a very easy integral to do. Emma?
Why do you square it?
Because I'm old and I make mistakes. Okay, very good. There is no square. Thanks. Anton, do you have questions or did you forget to lower your hand?
Sorry, I forgot.
Oh, okay, yeah, that's fine. All right. Is this problem clear? Okay. There's no uniform way for me to tell you how to do work problems. It varies from case to case to case. Okay. We will not test this thing in the exam. So for now, it's more just showing you how calculus can be applied to physics and other fields. Okay. So try to make sure that the concepts are making sense, but for calculation, we really don't care that much. Okay. So the concept should be making sense, right? If you have something which is changing, you don't have a constant, you just cut them into pieces. On each piece, you have a constant. Okay, then you just sum them together. But when you have infinite many pieces, when I say sum, you do integration. All right. Let's try another one. This time we have a tank. Okay. A tank has the shape of a inverted coin with height 10 and the radius 4 meters. Okay. It's filled with water to a height of 8 meters. How much work is required? To pump all of the water to the top of the tank. All right. Here is the tank here is the level of water below the red part. Okay. Now what you do is you take a pump. Okay. To drain all the water up. Okay. I wonder how much work is needed for this. That will determine how big of the pump you want to buy from Home Depot. Right, a bigger pump give you shorter time, a smaller pump give you all forever. Okay, so it really depends on how much work you are looking for. You need to go ahead and try to look for the corresponding pumps from Home Depot. So this is very important. Okay. Now again, force times distance, and you can see where you have trouble. Number one, what's the force? Gravity. Right, you need to go against the gravity and pull the whole thing, so equally to the gravity. Number two, how much distance? Well, it really depends, because if you think about it, the waters are at a different height. For the water here, how much do you pump? You pump this much for the distance, right? For the water here, how much do you pump? You only pump this much, which means fewer work, smaller distance. So at a different level, you have different level of distance to pump up. That's number one. Number two, how much force? Well, for this one here, you have a disk of water. You have a smaller disk of water compared to what you have here, because that thing has a bigger radius. Sounds good? So as you move forward, you have a smaller force because you have fewer water. Okay. As you move forward, you have a longer and longer distance. So both distance and the force are changing according to which location, which height you are. Sounds good? And now we want to sum all these works together. That's our goal. So let's set up the coordinate. I'm going to use triangles this time. I'm going to call this direction X. Okay. Now what you want to do is you want to cut them into pieces. Okay. And what you want to do is you want to integrate from 2 to 10 because all the water go up to 2. Okay. The work needed for each water disk depending on which disk are you talking about, you have different work and you sum them together. Sounds good? Okay, now we only have one thing left. That is, we just need to figure out how to quantify the work done by this disk with a distance x from the top. Then we let x run from 2 to 10. We have everything. Sounds good? All right. So how much work is done by this disk? Force times distance. Okay. What's the distance? The distance is x. Right? The bigger the x, the more work, the more distance you travel. Great. What's the force? The force is going to be gravity, which is mg. G is a constant. Fine. What is m? M is density of water times the volume of the water. Okay. What's the volume of the water? What's the shape? It's a disk, right? If it's a disk, your volume is pi r square h. Sounds good? Now you just need to figure out r and h. Let's draw it. You have this thing here. This is your h. Can you see your h is dx? or delta x before you take the limit. That's how thick this thing is, right? So the only thing left is r. And how do you figure out r? Can you see by similar triangle, you can easily set up this and get your r to be by a similar triangle. Therefore, that's your force. That's your distance. So together, your final work is going to be integration. 2 to 10, rho pi this dxg times x, which is 2 to 10. Okay, rho is 1,000 for water. 4 over 25, 10 minus x squared. dx times g is 9.8 times x. And finally, all the numbers, all the variables. Okay, this looks fancy, but it's nothing but just a number. Use a calculator, you can figure it out. So the key is how to do the integral of this, which you can do by yourself. All right. Is everything clear? From here, you can see that it does vary from cases to cases. Okay, there's nothing in common between different problems. That's why I say we probably just go over 2 examples to let you see the procedure. The key takeaway here is once you have something that is not constant, that something is changing, what you need to do is just cut them into small pieces. On each piece you assume is a constant, you just sum them together using integration. Okay. That will be the last example we go over in class. You have 4 examples, 4 web work problems. And once you finish that, I would say this section is over. Okay. Hopefully you see the importance of doing calculus in situations like this, because you see those kind of situations all the time in real life. It's not just a simple multiplication because things are varying. Any questions? All right. Try to do the web work. You will find it challenging at first. I mean, following my thoughts is easy. Establishing those kind of thoughts takes some time. So if it takes a long time for you to do one problem, it's normal. Okay? The good thing is we only have 4, so it's doable. Some other situations for you to think about. For example, if you're standing on a ceiling and try to pull some chain up to the ceiling. Can you see different part of the chain actually travel for different distance? So the total work needed, you have to do the integration because it's varying. Same thing if you're doing rock climbing. Wow, you're doing rock climbing, and you can see your feet. If you go to a certain height, right? Your head will go there right away because it's very close to the top. Sounds good? Your feet will travel a longer distance. So your feet do a different distance of work. Meanwhile, your head is heavier than your feet in terms of density. So what you're doing here is basically, if you want to calculate the work, you just cut yourself into pieces. You use the mass of each head disc, travel a small distance, plus your stomach disc, travel for a half distance, and plus your feet disc, travel for a long distance. You sum all of them together, again, through doing integrations. Sounds good? Another situation. You have a charge, an electron or something like that, but not electron, a proton. Okay, what you have is another charge coming to this one. So what's going to happen? They are going to repel each other. Good so far? Okay, and as they move closer and closer to each other, they repel stronger and stronger. Finally, eventually, this one stops somewhere. And then after that, this one starts to actually move back. Sounds good? So how much work is done by that proton through this process? Okay. You have to take the integration because your force is constantly changing. The closer you are, the bigger the force. Okay, so there's no way you can do a simple calculation by just multiplying two things together. You have to do the integration. And it's constantly changing. Okay, there are more and more examples like this if you just go deeper in physics. But I think you got the idea. So this situation is actually everywhere. So do the integration is the key. All right. That's everything we have for 6.4. Any questions before we move on to the last section? Okay, if no question, let's quit today. Tomorrow we start the last section. It only takes us like, I think 30 minutes to finish. And after that, the whole semester is over. All right.